Hey students, welcome to the first lecture of Linear Algebra 1 in the G30 program of Nagoya University. Since we are still living in these special times, these lectures will be recorded, but we will also meet once a week in Zoom in the tutorial. And also tomorrow, one day after this video goes online, we have a special meeting and where I will discuss everything you need to know about this course. So in this video I want to focus on the content of the lecture. But you can also find all information here on my homepage. So you see here on the top that there's a Facebook group where I think most of you already joined. But also if you don't have Facebook, I will announce some information in the NUCT course page. And here on this homepage you can also find all materials. So far there's not so much, but from tomorrow there will also be some course information containing all information on gradings and homeworks and so on. And then there will be some overview notes, lecture notes, and also from tomorrow or from after this video, you can find this video here under lecture videos. And also already the first homework is online on the homepage. And on the bottom you can find a schedule where for each week we have one topic, and for each week I want to record one video. So in this video here we will talk about linear systems. But first, so let's talk about linear algebra in general. So what is linear algebra? So if you would need to describe linear algebra in one sentence, then this would be that linear algebra is the study of solutions of linear equations. Which sounds maybe not so interesting, but linear algebra is really the foundation for a lot of theories in mathematics, but also in natural science and engineering. So, but more precisely, it's not just the study of solutions of linear equations. We will be interested in two main objects. So the main objects we are interested in are the following. So the first are some certain spaces. So these are, you can think of being flat spaces. And more precisely, these are called the vector spaces. And in linear algebra 1, we will mainly deal with something which is called Rn, which means just that, for example, we are considering the plane or a line or the three-dimensional space. So, for example, lines, planes, a three-dimensional space, and so on. And then the second thing we are interested in are maps between these spaces. Which are called linear maps. And for example, in three dimensions you can think of rotations or projections, and these are examples for linear maps. So for example, rotations, projections, and so on. And then we will also talk about some applications of these vector spaces and these linear maps. But before we start with, so at the beginning we will talk a lot about linear equations before we can go to the fun stuff. But first I want to give an overview of the whole semester. So here I have this, what I call the Linear Algebra 1 roadmap. So here we will start in the first 2 weeks. We will talk about these linear systems, which I will introduce today. And then next week we will talk about matrices and vectors. So what is a linear system? So I will define it in a second precisely. But for example, this here is a linear system. So we have two linear equations. So we have here these variables x1 and x2, and here's one linear equation, 2 times x1 plus x2 equals 1, and this is another equation, and then these two together form a linear system. And then next week, so first we want to solve this linear system, so we want to find all possible values for x1 and x2, such that both of these equations are satisfied. And next week then we will describe these equations by using matrices. So instead of writing two equations, we will write this product of a matrix as a vector equals a vector, And so this is just another way of writing this. So in this we will do in the first 2 weeks, and then in the week 3 to 8 we will talk about linear maps. And one example of a linear map will be just the multiplication with a matrix. So in general, a linear map will be something which maps from one Rn to Rm. So for example here, this element here, this vector with 2 entries, is an element in R2. And this here is also an element in R2. And here, this is a matrix. So this is a 2 by 2 matrix, which we will denote by 2 by 2. And here we multiply a matrix with a vector and get a vector. And this will be an example here for a linear map as a map from R2 to R2. And in general, we will define a linear map by a map which satisfies a certain condition. But then we will see that basically all linear maps are just given by multiplying vectors with matrices. And there's a lot to say about linear maps, so that's why we will talk a long time about these linear maps. And also in this period we will have a midterm exam on this. And then we go on, and from week 9 to week 10 we will talk about so-called subspaces. And one example here for subspace is, for example, this guy here. So U is the set of all tuples x1 and x2 such that x1 plus x2 equals 0. And if you would draw this here in this two-dimensional plane, then this U would be this pink line here. And we will see in general that subspaces are given by lines or by planes or by three-dimensional objects and so on. And in this time we will also talk about a so-called kernel and image, which will be properties of a linear map, and both of these will also be examples of subspaces. And then we will go on and we'll talk about so-called bases. So for example here, even though we don't know what this is yet, but this is an example of a basis in R3. And a basis basically just means that you can write everything as a linear combination of elements in your basis. And we will talk about linearly independence. But let's move on. Then at the end we will talk about orthogonality, which basically means if I have two vectors, for example u and v, and if they are orthogonal to each other, this means that the angle between them is 90 degrees. And we will describe this by using this so-called dot product, which means that the dot product of two vectors, which gives a number, is 0 if and only if these two vectors are orthogonal to each other. And then with this we will do a lot of applications. So for example, if you do an experiment and you collect some data, then we will use this theory from this chapter to interpolate our data points. For example here, one can imagine that one measures some data points here, these purple lines, and these purple points, and we are interested in the best fit, meaning the curve in the middle which interpolates these data points in the best way. And for this we will use this concept here of orthogonality. And also we will see that, for example, if you want to understand how 3D graphics on the computer works, then we will also see, for example, how can I draw a three-dimensional cube on a two-dimensional plane like a monitor. And this will also use the theory of linear maps and orthogonality. And then after this we will have a final exam, and some of you will move on to linear algebra 2. But today, of course, so we will start slowly and just talk about linear systems. So we will talk about something like this. Okay, so let's start with the real lecture, and let's start talking about linear systems. So first of all, this R here, this denotes the set of real numbers, and these are basically all numbers you considered in high school. So this, for example, contains the number 1, -1, or also fractions, so rational numbers 1/2, but also, for example, square root of 2, which is not a rational number, pi, e, and so on. So all possible numbers you dealt with in school is contained in this set of real numbers. But also in the lecture notes I gave some link to a reference where you can see that one can be really serious about defining what a real number really is. but in this course we will just assume that everyone knows what a real number is. And maybe at some points, maybe some of you also know complex numbers, or most of you will learn about them in the second year. But we will mention them at some points, but in this course we will basically just talk about real numbers. Okay, and with this we can now define what a linear system is. So first, if we have some real numbers, a1 up to an, so we have n numbers here, and an additional number b, then an equation like this we call a linear equation. So one example we saw before, for example, 2 times x1 minus x2 equals 4 would be an example of a linear equation. And in this case here a1 is 2, a2 is minus 1, and b is 4. And then if I have a collection, a finite collection of linear equations, this is what we call a linear system. So for example, if I have this equation here, and I have another equation, x1 plus 2 times x2 equals 6, then we will denote this by using these brackets and saying that these together, we consider them as one pack. So this is our linear system. So this linear system has 2 linear equations. And then a solution of a linear system is a simultaneous solution to all of its equations. So in this case, the solution of this linear system here are all possible values of x1 and x2, such that both of these equations are satisfied at the same time. And then our main goal is, and we will see that this solving linear system has a lot of different interpretations, but first of all we will just solve them and then later think about why it's interesting to solve linear equations. So the goal is to find all solutions. To a given linear system. Okay, so let's start with one example, with one linear system, and let's try to find all of its solutions. So this is example number 1. So here we have a linear system with 2 equations and 2 variables. And maybe at this point you can also stop the video and just try by yourself to find the solutions. So all possible values of x1 and x2 such that these equations are satisfied. And then you can check later if you did it correctly or not. And at the beginning we want to really make it precise and be careful and do it systematically. So in every step we want to write down what we are actually doing. So if I have 2 equations like this, what I want to do is I subtract and add these equations to each other such that in the end I can read off the solutions easily. So for example, in this case here, in both equations I have x1 and x2. So my first idea would be to maybe eliminate this x1 in the second equation. And for this, what I could do is I take 2 times the first equation and add it to the second equation. And the way I want to write this is I put a 2 here, and then I say 2 times this equation I add on top of this equation. And then I say, so this here means this implies. So if I do this, what I get is, well, the first equation I didn't touch, so it's still x1 plus 3x2 equals 1. And in the second equation, I now get rid of this x1, but I also add 2 times 3x2, so it's 6x2 to this. So here I have 7x2. And on the right hand side, I add 2 to 2, so it's 4. So this gives a new linear system. And now well, we can almost see what x2 should be in this case here, but let's do it slowly. So in this case we have 7 times x2 equals 4. So the next thing I want to do is I want to divide by 7. So I will just write here this 1 over 7 here, which means I just multiply this equation with 1 over 7. So this gives, well, again, the first equation stays the same. But now here I have x2 equals and then 4 over 7. So here I can already see what x2 is, and I could plug it in here and see what x1 is. But the more systematic way is to get rid of x2 here in the first equation. So now if I take 3 times this equation and subtract it from this equation, then I do not touch this x1 here because there is no x1. So I really just erase the x2 here. So I want to take minus 3 times this, and I put it on top of this one here. And this implies that the first equation is x1 plus 0 times x2, so this equals 1. And here I just have this is not 1. Here I take minus 3 times this, and I add it to 1, so this is 1 minus 3 times 4 over 7. So this is 12 over 7, and here I have 7 over 7, so this is minus 5 over 7. And here I still have this x2 equals 4 over 7. So this gives this linear system at the end, but here we just see that, well, this is an easy to solve linear system. We see that x1 equals minus 5 over 7 and x2 equals 4 over 7. But now the question is this actually a solution to the original linear system? And the answer is, well, in other words, do these two numbers satisfy actually these two equations? And the answer is yes, because all these steps we did can also be reversed. So we can also go from there back to there. So this gives a solution to the original linear system. Because every step or every operation also works in reverse. So in other words, if we would start with this linear system here, that x1 equals minus 5 over 7 and x2 equals 4 over 7, then what I could do, well, what is the opposite of adding 3 times this equation to this? Well, it means minus 3 times. So this means if I would add 3 times this to this, then what I get is x1 plus 3x2 equals 1, because 12 over 7 plus minus 5 over 7 is 7 over 7. And here we still have x2 equals 4 over 7. And then we could multiply this with 7, which is the opposite of multiplying with 1 over 7. So this implies x1 plus 3x2 equals 1, and here it's 7 times x2 equals 4. And then we could subtract this first equation 2 times from this one, which then gives 1 x1 plus 3x2 equals 1, and here minus 2x1 plus x2 equals 2. And therefore these two numbers. So if x1 is minus 5 over 7 and x2 is 4 over 7, then they also satisfy this equation. So these two linear systems, so the simple one and the one we started with, they have exactly the same solutions, because all of these steps we did were invertible. So therefore we have this equation here. So this is satisfied, and now we can use this symbol here, which means if and only if. Sometimes also just written if with 2f. So this is the case if and only if x1 is minus 5 over 7 and x2 is 4 over 7. So all the solutions to this linear system is just this one solution. Okay, so maybe in this simple case one could also do it directly by solving this one here for x2 and then plugging x2 into this one and then get a value for x1 and then plug it in again here. But for the beginning it's really important to do it systematically and also make sure that it's clear what step is done what you do in each step, because the equations get more complicated, and in the end we really want to get to a specific form, which is called the row-reduced echelon form. So but first let's do a more complicated example. So this is example number 2. So now we have 4 equations and 4 variables, and we now want to find all equations. We want to find all solutions, sorry. So what did we do in the first example? Well, the first step here was to somehow get rid of this x1 in this equation, and then in the rest we just had x2 and we could find the solution. So here it's the same idea. Now we have the first variable is x1, and it still appears here in the second and the third equation. So the first thing we want to do is want to get rid of x1 in these two equations, and here the fourth one we don't have an x1, so we don't need to worry about this. So therefore, to get rid of this one, we need to take 3 times this equation and subtract it from there. So we will write, we take minus 3 times this equation and add it to this one. And for the second one, we need to take it 2 times and subtract it from there. So we take it minus 2 times, and so this indicates now that we do 2 steps at once, and what we get is the following. So first of all, the first equation is the same, and also the last equation, because we didn't touch it. And now in the second equation we get rid of this x1 here, but now we need to take this minus 9 times minus 3, which is plus 25, and plus 27, and then we subtract 2, so here we get 25 x2, and then the rest you can check by yourself that this gives 10 times x3 minus 5 times x4 equals minus 10. And the third equation, we get rid of this x1 and we get 25 x2 plus 10 x3 minus 5 x4 also equals minus 10. So now we don't have an x1 anymore in the second, third and fourth equation. And the next thing we want to do is we now focus on x2, and we say we want to have an x2 in the second equation, but we want to get rid of x2 in the third and fourth equation. So in this case it's easy to see what we need to do, because they all have the same coefficient here, namely 25. So what we do is we subtract this from there, and we also subtract it from there, and what we get is, so let me cheat again here with copying. Oops. So we have this here. So the first and second is the same. But now in the third, well, here we see that the third is exactly the same as the second. So here we actually get the equation that 0 equals 0. And here we get rid of this. And here we still have an x3. Well, minus x3. So this is minus x3 plus 3x4 equals 6. And now what we see here is we have this really uninteresting equation, because this doesn't contain any information. So this equation we can now forget in the following and really just focus on these three equations with 4 variables. So now we have an x1 here, an x2 here, and an x3 here. And the first thing we want to do is now to get rid of this minus 1 here. So now we have x1 just appears here. Here we have x2, which appears in these two, and x3 appears in all 3. So now what we want to do is we want to erase x3 in these ones, because I can take this equation here, which doesn't contain x2 and x1, and I can use it to get rid of these x3 in these equations. Because, for example, here, if I take now 10 times this and add it to this equation, then I get rid of this. And if I take this 3 times and subtract it from, or if I take it 3 times and I subtract add it there, subtract it from there, then I also get rid of this. So I take minus 3 times this, and I add it to this one here. And so in the beginning for x1 and x2 nothing happens, because there is no x1 and x2 here. So we have x1 minus x9 times x2, and now there's no x3 anymore, but we also take this minus 3 times 3 is minus 9. Minus 9 plus 1 is minus 8. So this is minus 8x4. And also minus 3 times 6 plus 4 is minus 14. And in the second equation, the 25x2 is also still there, because he has no x2. But we got rid of this x3 part here. And here 10 times 3 minus 5 is minus 20, is plus 25, so this is plus 25x4 equals, and then 10 times 6 minus 10, so this is 50. And the last one is the same, which is minus x3 plus 3x4 equals 6. Okay, so now x3 just appears here, and first we will clean up a little bit and get rid of this minus sign and this 25 here. So here we will divide by 25, and here we will multiply with minus 1 to get x1. So the first equation, I can steal it from here again. Oops. So this equation is still the same, but here we now have 1x2 plus 1x4 equals 2. And here I just change the sign. Oops. So this is x3 minus 3x4 equals minus 6. So, and now what is the next thing we want to do? Well, x3 is now alone here, so there's no x3 here, but x2 still appears here in these two, so we want to erase x2 also in the first equation. And so to do this, we take 9 times this and add it to this equation here. And this gets rid of this x2 and also changes these numbers because 9 times 1 minus 8, this just gives x4. And 2 times 9 minus 14 is 4. So we end up with this equation here. And now we are basically done. So this is actually the form we want to reach. So I also want to give this a color and a name. So this is, I call equation star. Because now we can actually see what the solutions of our linear system is. So first of all, we notice that all of these operations we did, we can also reverse. So for example, here, instead of adding 9 times this equation to this, we could subtract this equation 9 times from there. So actually all these things here go in both directions. So everything is, we say everything here is equivalent. So all the solutions to this linear system here are the same as the solutions to this linear system here, which we want to solve. But here we can already see what the solutions are, because here in the first equation, this is the only equation which contains x1. So this x4 could be anything. So if we know a value for x4, we can also get a value for x1 because we just subtract the x4 from the 4. And in the second equation, x2 is the only variable appearing in the second equation. So also here, if x4 has some value, we can get the value by of x2 by subtracting x4 from 2. And in the third equation, x3 is the only variable which appears in the third equation. In the third equation is the only equation where x3 appears. So we see here that this x4 can be arbitrary, and if we choose some value for x4, we can get a unique value for these x1, x2, and x3. So the variable, so can be chosen arbitrary. And what we usually do is we say that x4 equals t, where t is just some real number, so it's like a parameter for our solutions. And if x4 equals t, or maybe you can choose your favorite number for t, then we get the solutions as follows. So all the solutions So what is, if x4 is t, what is x1? Well, we can subtract x4 from there. So we see that x1 equals 4 minus t. And x2 equals, well, we can subtract this t from the 2, so it's 2 minus t. x3 is, well, minus 6 and then plus 3t, so minus 6. Plus 3t, and x4, well, x4 is t. So we see that in this case, we not just have one solution. For each arbitrary number t, we get a solution given by this here. And this gives all the solutions of our linear system here. Okay. And so we somehow see that here in this equation, in this final equation here, there are two types of variables. So we have these variables which just appear alone in one equation. So this is the equation for x1, and this is the equation for x2, and this is for x3. And but we also have this equation here, which can be chosen arbitrary. And these also have names. So in this equation, in this purple star equation, so each equation contains a variable that occurs just in this equation, so that occurs in no other So in our case, we have this x2, x1, x2, and x3, and these are called pivot variables. So we have here our pivot variables, but then we also have this the rest, the other variables. Well, in our case, we just have one. So in this example, x4 are called free variables. Let's take green, free variables, because they can be chosen freely. So this is the free variables, and these are the pivot variables. And in general, the free variables can be chosen arbitrary. So in this case, we just have one free variable, but it could be that there are several free variables, and then we can choose the one we say is the value t1 and the other is t2. And then depending on these free variables, we can get a value for these pivot variables by solving these equations with using these free variables, like we did here. Okay, and now we want to write down this algorithm we used here, and first we want to give these operations we did, we want to give them a name, and these are called elementary row operations. And there are three types of elementary row operations. And the first one, which we denote by R1, is that we add. So if we have a linear system, meaning we have a finite collection of linear equations, then we can apply one of these three row operations to this linear system and get a new linear system. And the first row operation, R1, is adding a multiple of one equation to another, which we did, for example, here. So here we used this R1, adding 9 times the second equation to the first. And another elementary row operation is multiplying one equation with a non-zero number. And here it's really important that we just allow non-zero. For example, like we did here, in this case we multiply this equation with 1 over 25. And why it's important that this is a non-zero number, because if we would multiply with 0 here, then we would get the equation 0 equals 0 here. But this multiplying with 0, we couldn't go. We wouldn't be able to invert. So from the equation 0 equals 0, we wouldn't be able to obtain this equation here. So it's really important that these operations are also invertible. And this is the case if we multiply with a non-zero number, because every non-zero number can be inverted. And then the last row operation, elementary row operation, is just changing the order of the equations, which we didn't do in this example here. One could imagine that if this equation would be on top here, then we would maybe change the order of this equation and this equation, because we want to have the x1 in the first equation. And because all of these operations are invertible, so we can go back. If I start with a linear system and apply these elementary row operations, I get a new linear system. And because it's invertible, the solutions of these two linear systems are the same. So therefore, we will have this proposition here, which we will make precise later and don't give a precise proof now. But I think it should be clear by the fact that these operations are invertible, that if I apply an elementary row operation to a linear system, then this does not change the solutions of these linear systems. And therefore the goal is, if we start with a linear system, we want to apply the correct elementary row operations to find in the end an equation which is in this form, which is called the row-reduced echelon form. Row-reduced echelon form. And this will be part of the first homework, where the exact definition of a row-reduced echelon form is given. And later we will define this also for matrices. And from this row-reduced echelon form, we can read off the solutions of our equation by saying that these variables which are alone are the pivot variables, and these variables which are not alone, these are the free variables, and the free variables can be chosen arbitrary. And then after we choose them by saying this is T1 and this is T2 and this is T3 and so on, we can then give a value for these pivot variables, and this will give all solutions to our linear system. And now what we want to do is describe this algorithm which we did here. So there's a name for this. So the general solution method for a linear system is called Gaussian elimination, which is named after Carl Friedrich Gauss, a German mathematician, even though this method was already used by Chinese 2000 years ago. And if you go to the Wikipedia page of Gaussian elimination, you see also some notes on the history. So there's some strange reason why for some people it's called Gaussian elimination, but also often you can find the notion of the word row reduction. But anyway, because I'm German, I need to mention this guy here, because it's a quite famous mathematician, and yeah, this is how usually this this method is called. But even though this funny guy here didn't really invented it for the first time. So how does this look like? So there are several steps, and there's one way down and then one way up. So we saw in our example here, what we did first is we wanted to put the x1 here in the first equation, which was already there, and then we wanted to erase it from the rest. Then we took care of the x2, erased it, and then we had the x3. And then from here on, we wanted to go up again and erase x3 here. So we erased it there, and then the x2 there. So we first went down and then we went up again. And therefore, what we first do is going downwards. And the first step is make the first equation contain the first variable. And this we can do with the row operation R3, which just means we can change the order of the equations. So this is the first step. We want to make sure that x1 appears in the first equation. And then we make the coefficient of this variable equal to 1, which we can do by R2, because R2 is just multiplying with a number. So if there is 2 times x2, then we multiply by 1/2. And then we can eliminate this variable from the other equations. And then after step 3, this x1 just appears in the first equation. And then we can iterate this, so we can go back here and then talk about x2, or the next variable which appears. It could be that x2 doesn't appear anymore, but the first appearing variable in the second equation, or the first appearing variable we want to put in the second equation by changing the order of equations, and then remove it from the equations below. And then also make the coefficients 1, and so on. So in the end, after this downward process, we have an equation which looks something like this. So maybe we have some x1 somewhere, and then maybe we will have some stuff here. And in the second equation, so this is just, it could be that we have some x2, x3, and x4, and so on. And then maybe in the second equation we have x4. and here everything is 0. Well, maybe not there. And then we have some stuff here. And then in the third equation, at some point, we have the next variable, let's say x6, and some stuff here. And now we have for each equation starts with one variable with the coefficient being 1. And now we want to make sure that these variables do not appear in the other equations. So therefore we want to go to this upward step. So again, let's go back to this example here. So this is now the situation after the downward step. Well, not quite yet, because there's still a 25 here. But now, after this step here, we want to make sure that x3 is just in the last equation. So we want to erase it from there. We get this, and then we want to make sure that x2 is just in the second equation. So therefore, the upwards step is we start from the bottom, and we look at what is the first variable appearing. So for example, in this example here, it would be x6. And we want to eliminate it from all other equations above. And this we can do because in front of x6 here is nothing. So I can take this equation and remove all the x6 terms in this equation and this equation by taking this x6 and adding a multiple of this x6 of this equation here to this equation and this equation. So we can use the row operation R1. So after this step, there's no x6 here, and then I go to the second equation. So I go to the one equation above, and I make sure that this x4 does not appear in the equations above. So I can also remove this x4 from this. And after doing this, we are actually in this situation like here. There will be some free variables which appear maybe in all equations, but each equation starts with one variable with a coefficient 1, and these variables do not appear in any other equations. And these are then the pivot variables, and the remaining variables are the free variables which we can choose freely. Okay, so let's do a final example for this, and again try to stop the video here and apply this algorithm to this linear system here. So we want to find all the solutions to this linear system, and we start with these downward steps. So the first step is we want to make sure that the first equation contains the first variable. Well, in this case, this is not the case, because here in the first equation we don't have this x1. So what we want to do here is we want to swap these two equations. So we use row operation R3. And this gives, let me cheat again, this gives this. This linear system. Okay, and then what is the next step? Make the coefficient of this variable 1. Well, in this case here there's a 1, so we don't need to do anything, but if there would be a 2, then I would just multiply this equation by 1/2. Third step, eliminate this variable from all other equations. So I want to eliminate x1 from the rest. So here's no x1, so I don't need to do anything, but here's an x1. So I want to take this equation times -1 and subtract it from there. So this is row operation R1. And this gives, where the first two equations are the same. And now there's no x1. And also x2 vanishes here. And x3, so I have here -2 times x3. And plus x4. And 1 minus 0 is 1. Okay, so now we are in this situation where x1 just appears in the first equation and nowhere else, and the coefficient is 1. So here in this algorithm we finished these 4 steps for x1, and now want to go back here and do the same for the next appearing variable. So if we look here, the next appearing variable is x3. So what we want to do is so assume that there was no x3 here. Then we would swap these two equations here, because we want to make sure that x3 appears in the first equation. And now the next step is to make sure that the coefficient here is 1. So we multiply by -1. So this is R2. So I just change the signs here. And now we want to erase x3 in the remaining equations. So always remember, we don't think about the first equation, we are just in this part here. So we want to erase x3 from the equations below, and this we can do by adding 2 times this to this. So this is again row operation R1, and what we get is, well, this first is still, well, second is also the same. So let's put it here. So there's no x3 anymore, and there's minus x4 here, and yeah, and 1. So now x3 here in the remaining part just appears in this equation and not below, and therefore we finished these 4 steps these 3 steps for x3, and we now go to the next equation, or we just consider this linear system below, which is just this part here. And now we just want to make this -1 and 1, so we multiply it by -1, which gives this linear system here. x4 equals -1. And now we finished this downward thing, because now in each equation starts with one variable which does not appear below. And now we want to go upwards and make sure that this variable also does not appear in the equations above. So we now go into this upwards part here, and we now start at the bottom and look at the first variable which appears, and then want to remove it from the equations above. And in this case here it's x4, so we want to remove it from there and there. So we added 1 times to this equation and 1 times to this equation. And then what we get is because there's nothing in front of x4, everything here doesn't change, so it's x1, x2 plus x3. And now we remove the x4, so this is just 0. And in the second equation we have x3 equals, and now -1, because we add -1 to 0. And here we have x4 equals -1. So we now finish the first upward step for x4, because we made sure that there's no x4 here. So we now want to do it for x3 and make sure that x3 does not appear above. So we take this part here, -1 times there, and all these steps are always R1. So here we have x1, x2, and we remove the x3 there. So this is just, so here we have 1, because -1 and -1 oh, well, I'm stupid, sorry. So we also have here it's -1, because here we also added the -1 there. So if I subtract the -1 there, I also have a 0 here. Sorry. And here we still have x3 equals -1. And here we didn't do anything. Okay, and this is our final form. And now, so this is now in so-called row-reduced echelon form, because now every equation starts with one variable which does not appear in any other equation. So this, and this are the pivot variables. And the remaining variables, in this case x2, is free variable. So what we can do to find the solutions is, we can say x2 is some real number. And then the solutions well, the first equation is the equation of x1, so we can solve x1 by using these free variables. In this case, it's just minus x2, so x1 is minus t, x2 is t, x3 is, well, x3 is just -1, so it's -1, and x4 is -1. And this t is now some arbitrary real numbers. So all the solutions for this linear system is given by this. So if we choose an arbitrary t, then x1 needs to be minus t, x2 needs to be t, and in x3 and x4 are always -1, independent of the choice of this t here. Okay, yeah, and that's actually all for the first lecture. We now talked about these linear equations, or these linear systems, and how to solve them. And next time we will describe these linear equations using matrices and vectors, and then, but again, talk about how to solve these equations by talking about the row-reduced echelon form of a matrix. Yeah, so then see you in the Zoom meeting, or yeah, see you next week. Bye bye.